All right. So, good evening and welcome to the fifth live session for Multirate DSP. My name is Avik Mukhopadhyay and I'm one of the instructors uh, for this course. So, we'll be discussing some sample problems that were covered in the week number 5. So, if you go back to your lecture videos in the fifth week, basically uh, the applications of multi-rate DSP were explored, and mainly the analysis of the filter banks. Filter banks was carried out, and we saw the spectral analysis of filter banks. Then we got a flavor of DFT and high resolution spectral analysis, and we also looked at something called the transmultiplexer, which converts the TDM to FDM and vice versa. So and we just briefly introduced the idea of maximally decimated filter banks. We just introduced that terminology. We haven't looked at that. So with all these concepts in mind, let's begin our today's session. Um, so I believe you can see question number 1 on the screen. Um, so I'll just start. Okay, so please read the first question. So all these numerical problems are based on the concepts that are covered in the lectures. So if you guys are clear with the concepts, then you should be able to solve these problems. But anyways, the purpose of these live sessions are to uh, guide you with the approach to how to approach these kind of problems, so that you can solve the assignment questions and also hopefully do good in the exam. Okay, so I hope you have gone through the question. So, and in fact, this is a very similar problem which was discussed in the lectures as well. So, you see, we have been given three input sequences x naught of n, x1 of n. There are two figures, okay? The figure on the right, we have this block diagram where three input sequences are fed to an upsampler of factor 3. Then it is further passed through three filters, f0 of z, f1 of z, and f2 of z. And these filters, if you see the sentence on the bottom, it's mentioned that these are ideal brick wall filters, uniform synthesis filters. Synthesis filters because, as the term suggests, the terms implies synthesis, it means it's used to synthesize, it's used to, they're getting combined, these individual signals are getting combined to synthesize a new signal. That's what is happening. So you see, from x0 of n, x1 of n, and x2 of n, we are combining them through some processing and filtering to generate a new sequence which is y of n. That's why synthesis filters, and these are like the two broad categories of filter banks as well. This is the synthesis filter bank. The other class is the analysis filter bank, where you decompose or split one sequence into multiple sequences like that. That's the opposite of this. So anyways, so these three filters, f naught of z, f1 of z, and f2 of z, are ideal brick wall filters, meaning that they are just ideal rectangular filters, and their corresponding center frequencies are also mentioned. F naught is centered at omega equals to 4 pi by 3, f1 is centered at 2 pi by 3, and f2 is centered at 0. And each of these filters have a double-sided bandwidth of 2 pi by 3, meaning that like its bandwidth of each of these filters is 2 pi by 3. That's the width. Okay. And given this information, and also you are if you look at the figure on the left, the spectrum of the three input sequences are given on the figure on the left. Okay, how do they look like? And all of them are band limited to, you know, from minus pi to pi. Then given all this information, we are asked to find the spectrum of the sequence y of n, that is y of e power j omega. That's what you need to find. Okay, so how do we do this? We have in fact seen these kind of problems in our lectures, so we'll do it step by step. Okay, and please interrupt me if anything is not clear. Okay. Okay. All right. So I'll first draw the block diagram. So what I will do is I'll try to use different colors for the different sequences so that you are able to clearly visualize it. So first sequence was x naught of n, that goes to a upsampler, and then it is passed through f naught of z or f naught of e power j omega, whatever you call it. It's a filter. And okay, this is one of the branch. Okay, then there's another branch. Let me use a different color for the other branch. So then we have another sequence x1 of n, which also goes through similar blocks, an upsampler followed by a filter f1 of z. Okay, and yeah, we have this. And similarly there is the third one. So which should I use? Maybe use a different one. Then we have x2 of n. Okay, so this is f2 of z. Okay, and yeah, and they are basically getting added up. So you can think like, okay, this is the first incoming branch, and it gets added here. This is an adder, and then it further gets added down here at the lower branch. Okay, and this final output is the one which we want to study. So the spectrum of y of n is what we are interested to find. Okay, and since there are multiple blocks in each of this chain, so to arrive at y of n, we will go step by step from left to right. So that's why, like I have done in previous sessions as well, we will assign some names to these intermediate sequences. So in the first branch, the branch on the top, I'll call this intermediate sequence after the upsampler to be some x naught prime of n. Okay, and similarly the sequence after the filtering f naught of z, I'll call it x naught double prime of n. And I'll do the same thing for the remaining branches. This is x1 prime of n, this is x1 double prime of n. It's just a notation. Similarly, this is x2 prime of n and x2 double prime of n. Okay, great. Okay, so now what's given is we are given the spectrum of these three input signals x1, x2 and x0. So I'll draw that. So x1 looks like this, sorry, x0, the spectrum of x0 looks like this. So we have this from minus pi to pi, okay, and this height is 1. So this is the spectrum of x0 of n, that basically the DTFT of x0 of n. Okay, and this axis is of course omega, so the center is 0, right? And similarly we have the other spectrums as well, and I'll stick to different colors. Okay, so x1, how does x1 of e power j omega look like? So this is not exactly rectangular but like a trapezoid, so it's something of this form, and these are not drawn to scale. So yeah, this, okay, and this height is again 1. Okay, right. And finally the third spectrum for x2 of e power j omega, it looks like a triangular function. So it is also limited from minus pi to pi, and the peak is at 1, and yeah, this is how it looks. So these are the three spectrums, just a rough sketch of these three. This is all the information which is given in the question, and also we are given the information about these three filtering blocks, which is f0 of z, f1 of z and f2 of z. They are all ideal brick wall or rectangular filters, and their center frequencies are also mentioned and their bandwidths are also mentioned. So each of them have a bandwidth of 2 pi by 3, and the center frequencies are also given. So I'll just draw as per the information which is given. So I'll draw it here itself. Okay, so at first we have, I'll draw this omega axis. This is omega axis. At first we have f0, sorry, f2, let's say f2 is basically, as per the question, f2 is centered at omega equals to 0. I'll go back to the question. f2 is centered at omega equals to 0, and it has a bandwidth of 2 pi by 3. So it would look something like this, So this is from minus pi by 3 to pi by 3 because it is centered at omega equals to 0 and it has a bandwidth of 2 pi by 3. So this is how the spectrum of f2 of e power j omega, the magnitude spectrum of this would look like. and this height could be some constant k or whatever, we don't know. So this height is unknown to us, so I'll not mention it because it is not given in the question. So yeah, so this is f2. What about f1? F1 is also similar, but it is centered at 2 pi by 3. So f2, for f2, okay, so um, okay, f2, okay, this so, okay, what I have done here is I should have used the correct ink color. So what I will do is basically for x naught I have used blue ink, right? So for f2 I should use green ink. So yeah, I should have used green ink. So let me do that. Okay, let me do that. Let me do that. Let me do that. This is just for visualization purpose, and I am intentionally taking time so that it is clear. So f2 we drew, right? For the lowermost branch, it corresponds to x2. So we have used green color. So I'll redraw the same thing in green. So it's from minus pi by 3 to plus pi by 3 with the center at 0. Okay, this is mod of f2 of e power j omega. Okay, and now what about f1? It is same thing but centered at 2 pi by 3, and I will use red color. So like this, this this center is 2 pi by 3, and this edge would be at pi, again the same bandwidth, 2 pi by 3. Okay, and this is the second spectrum is mod of f1 of e power j. And I hope you are following, so that whenever I make mistake you should be able to point it out. And finally the third spectrum is centered at, which is f naught, is centered at 4 pi by 3. Okay, and these all are actually exactly adjacent. Okay, they are non-overlapping, but they are exactly next to each other. So um, they are touching basically, but not overlapping. So this ends directly at here. Okay, there is no gap in between them. Okay, so this is what the third one is, which is f naught of e power j omega. Correct? And then it again repeats. Then after this we will have f2 arriving again. Okay, because they are 2 pi periodic, right? So f2 will again follow this like this, and this center would be at 2 pi because it will repeat after 2 pi. So this is how the spectrums look like for the filters. I hope you are with me fine till now. Okay, now we will go step by step from left to right. So first x naught of n, if you look at the upper branch, this one, it passes through a upsampler to give me x naught prime of n. Now what does an upsampler do? This is an upsampling of factor 3. So it creates in the frequency domain, because we are interested in analyzing the spectrum. Okay, so in the frequency domain, the spectrum, in the spectrum, this upsampler will introduce L minus 1, which is 3 minus 1 additional copies between 0 and 2 pi. Okay, so basically 3 minus 1 is 2. 2 additional copies will be there, and we'll have multiple basically images. That's what happens in upsampling, right? And that's why we used an interpolating filter to remove the undesired extra images. We only keep the one, the desired, that corresponds to the desired signal, that is band limited from minus pi by L to plus pi by L. So yeah, so x naught prime of n will look like that. So basically for x naught of n, if we have the spectrum for x naught of e power j omega, since it is band limited from minus pi to pi, there will be multiple copies of such spectrums, but the edges will get compressed by a factor of 3. So this point minus pi and pi now will map to minus pi by 3 and plus pi by 3, and we will have multiple images next to it from 0 to 2 pi. Okay, so in case you are not able to follow, just revisit the old lectures wherever we have seen, where we have seen the upsampler and downsampler, how their spectrum looks like. So we are looking at the first branch, the branch on the top. We are trying to find the spectrum for x naught prime of n. Now, so how does x naught prime, where is the, so how does x naught, color should be different. We'll go back to blue color because we are dealing with x naught, the first branch. So x naught prime of e power j omega, the spectrum of x naught of n. What does it look like? It looks like something like this. So you see, from here, basically from here to, you're coming to this, and the change as a result of upsampling will be that these points, these minus pi and plus pi, they will get mapped to minus pi by L and plus pi by L, where L is the upsampling factor. In our problem it is 3. So these points will map to minus pi by 3 and plus pi by 3. And we will have L minus 1 extra copies from 0 to 2 pi. So which means we will have 2 additional copies. Okay. So that's exactly what we are going to draw. Okay. So yeah. So how does it look like? Okay. As we mentioned, it now gets, compressed like this from minus pi by 3 to plus pi by 3, and the height is unchanged, it is 1, and we will have extra copies, so extra 2 copies. So we'll have 1 copy here, this is centered at 2 pi by 3, this point is pi, another extra copy will be there, which would be centered at 4 pi by 3, this point would be 5 pi by 3. Okay, and finally the first copy, which is our original copy, centered at 0, will now repeat at 2 pi after 2 pi, right? So like this. So this is centered at 2 pi, and this is 7 pi by 3. Okay, and of course it continues, like it continues on the negative side as well, it will happen. And so the thing to see here is that these two in between spectrums, these are the two additional L minus 1 additional, L is 3, therefore 2 additional copies are present as a result of upsampling. Okay, so this basically is passed through. This is what happens when this is passed through an upsampler of factor 3. That's what we are doing in the top branch, right? Okay, now this one, now what happens to x naught prime of e power j omega? We are looking at the top branch, so that gets filtered through f naught of z or f naught of e power j omega, right? That will give me this x naught double prime of n. So what does the spectrum of x naught double prime of e power j omega look like after getting filtered? So the filters I have drawn here, this one basically, this figure. So these filters, okay, the f naught of e power j omega basically will filter this x naught prime of e power j omega. Okay, so can you tell me what would the output look like? Are you able to understand so far?
Yes, sir.
Okay, so then now basically what I am asking is this x naught double prime of n, this signal here, we are trying to look at its spectrum, basically x naught double prime of e power j omega. So you see x naught prime of n is passed through this filter, okay, to give me x naught double prime. So basically in the frequency domain we are basically multiplying the spectrum of the input with the f naught of z to give me x naught double prime of e power j omega, right? In time domain we do convolution, but in the frequency domain we have multiplication, right? So this x naught prime of e power j omega is now filtered through this f naught of e power j omega to give me x naught double prime of e power j omega in the branch on the topmost branch. So now I am asking you to tell me what does it look like? What does this spectrum x naught prime of e power j omega look like? So you have the f naught looking like this. See this figure here, f naught is given. You need to multiply this with x naught prime of e power j omega. So tell me what kind of spectrum do you get? So look at f naught of e power j omega. F naught of e power j omega is lying from my pi to 5 pi by 3, right? This band, correct? So if you multiply that with this x naught prime of e power j omega, only the portion from pi to 5 pi by 3 will exist, yes or no? Yes. Okay, I'm assuming you are able to follow. So it gets basically filtered by f naught of z. So only the portion from pi to 5 pi by 3 will exist. Okay, so what kind of spectrum do I get here? If I label this at 0, so from pi to 5 pi by 3. This portion will exist, and this is 4 pi by 3, centered at 4 pi by 3. So basically only this block, this spectrum, this copy survives, right? Because you are filtering it through f naught of z, right? So nothing special in this. And similarly what we are going to do is we'll be doing the same thing for the other branches as well. And finally, once we are done with that, we will add them up together, because y of n basically is the sum of these three incoming double prime, right? X naught of double prime plus x1 of double prime and x2 of double prime. So we'll add their respective spectrum to get the spectrum for y of n. So now you tell me, now similar to this what we have done for the topmost branch, you do the same thing for the um, second branch. So I'm just looking at the different color. So now we need to find this x1 prime of n and x1 double prime of n in the second branch. So now you tell me, what does x1 prime of e power j omega look like? Okay, so I have this. Yeah, so what does x1 prime of e power j omega look like? This is x1 of e power j omega, and this signal is passed through a upsampler of factor 3 to give me this output. So what does it look like? Same thing. What happens? Tell me. This is from minus pi to pi, band limited to minus pi to pi. So now after upsampling by 3, those edges will get mapped to which points? This is the same thing which I have done for the topmost branch. Tell me now, this point will be basically from minus pi by 3 to plus pi by 3, right? Basically it becomes from pi to pi by l, it becomes, gets compressed. Height remains the same as it is. This is centered at 0, and we will have two additional copies. Okay, so two additional copies. Two additional copies of this from 0 to 2 pi. This one is the first additional copy, centered at 2 pi by 3. Then we have another additional copy centered at 4 pi by 3. Then this is 5 pi by 3, and again it repeats this first copy, then again it repeats after 2 pi. Okay, so this is 2 pi again, and this point is 7 pi by 3, right? Again, so you observe that due to upsampling by a factor of 2, we are introducing these two additional copies. So that's what happens in the time domain. As a result of upsampling, you introduce L minus 1 additional zeros between every two samples. But in the frequency domain, what happens is that first of all, the spectrum gets compressed by a factor of L, but you introduce L minus 1 additional copies of the spectrum from 0 to 2 pi. Okay. So yeah, these are all just a revision for your previous lectures. So now this one is passed through the filter f1 of z or f1 of e power j omega. So we are looking at the second branch basically. So look, this second branch x1 prime of n filtered through f1 of z to give me x1 double prime of n. So for x1 double prime of n, right? So this filtering will basically give me the spectrum for x1 double prime of e power j. Now tell me, what does it look like? What does this spectrum look like? F1, I have drawn it here in red. You see, this is the reason I actually used some consistent different inks so that you can understand. Now tell me, F1, look at F1. F1 is from pi by 3 to pi. Now you tell me, after filtering through F1, what will I get? Yeah, just quickly tell me. F1 is from pi by 3 to pi. Look at this portion. This is my F1. So it exists only there, it is non-zero only there. So after multiplying the incoming spectrum with that part, I'll only filter out that portion, right? So only that portion will exist from pi by 3 to pi. So then tell me, how does the output spectrum look like? I'm not sure if you are able to follow or not, because I'm trying my best to make you understand, but if you're not responding, then I won't understand like if it's clear or not.
Yes, sir.
Yeah, then tell me like what's the output that you're going to get. I'm trying to figure out this x1 double prime of e power j omega. I am filtering this incoming x1 prime of e power j omega through f1. F1 I have drawn here. Three filters I have drawn here. This figure. F1 is the middle one. What is the band for F1? From which frequency to which frequency is F1 existing? Tell me from the figure.
So pi by 2 to pi.
Yeah. So if you multiply that part pi by 3 to pi, it is only non-zero in that band. So if you multiply this whole x1 prime of e power j omega with this filter, what are you going to get? That's what I am asking you. So you'll get basically only the part which corresponds to this region from pi by 3 to pi, because that's the portion in which the filter is non-zero. In the rest of the portions, the filter is zero.
Yes, sir. Yes, sir.
So you'll get something like this. So from pi by 3 to pi. And this height we actually don't know. This height of the spectrum will depend actually on the height of this filter, which is not given in our question, but it is some constant value. It's an ideal brick wall filter, it could be some constant value. So depending on that height, we will get the height of the output spectrum, but nonetheless it looks like this. and the center will obviously be the midpoint, which is 2 pi by 3. Okay, and same thing we'll do for the third branch, lowest branch. Okay, for the lowest branch we use the green color. First we will find x2 prime, then we will find x2 double prime. So we'll change the color to green. So x2 prime of e power j omega, that would look like, so again this x2 of e power j omega is present. So you take this signal and upsample that. Take this signal, upsample that by a factor of 3. Okay, to produce this x2 prime of n, or the spectrum corresponding to it. So again the same thing we'll be doing. So this time the shape is just different. It's a triangular function from minus pi to pi. So that gets compressed by a factor of 3 to a triangular shape from minus pi by 3 to plus pi by 3. And as usual we will have additional copies. By the way, in the previous branch also this is like it extends on the negative side as well, and for this one also it extends in the negative side as well. I'm just drawing it from 0 to 2 pi. So this will have its, again it's the amplitude remains the same at 1, and we will have the first extra copy. This is our first extra copy centered at 2 pi by 3. This is our second extra copy centered at 4 pi by 3, and finally it repeats at 2 pi. This is centered at 2 pi, 7 pi by 3. Okay, and again I'll mention that these two are our two additional copies. Introduced because of upsampling. Great. And again in the lowermost branch this gets filtered through f2 of e power j to give me another spectrum which I have labeled as x2 prime, x2 double prime, sorry, x2 double prime of e power j. Now if you go back to the filter f2, how does it look like? So the figure here in green, so this portion, this one, so it's from minus pi by 3 to plus pi by 3, and again it repeats at 2 pi. So it will select only that portion of the input spectrum. So it will select basically this part, and since it repeats at 2 pi, it will again select this part. Okay, so at the output you will have this. So this copy is selected. Height again we don't know, it depends on the amplitude of the filter. And again the last copy which is centered at 2 pi. So 2 pi, let me note somewhere here. So 2 pi would be like this. This is the drawing is not good. Yeah, something like this. So this is the last copy which is passed through, centered at 2 pi. Okay, so basically I have actually so this is the portions which are passed, and this is the portion which is discarded. So I'm labeling by tick mark and cross. Okay, and similarly for the previous um, branches also, this was the portion which got passed and this got discarded by the filter. Okay, and similarly for this one, this was the portion which got passed and the rest were discarded. Okay, okay, now we have everything. So we have the spectrums for this x0 double prime of e power j omega, x1 double prime and x2 double prime. So since these three signals are getting added to give me y of n, so the spectrum for y of n would also be the sum of these individual spectrums, right? So I'll go to the next page. So basically from our block diagram, what we see is y of n is the sum of these final sequences which are getting added up. So these three. Okay. And this is x naught. Okay. So my if I take the DTFT on both sides, my output spectrum y of e power j omega would be the sum of the individual spectrums of these, right? X naught of e power j omega plus x1 of e power j omega plus x2 of e power j omega. So of course double prime, yeah. So this is what, okay. So this implies this. Basically I have taken the DTFT on both sides. So now we already looked at the spectrums, how do they look like for x1 double prime, x2 double prime and x0 double prime. Now our task is to add them up. Okay, so you see you're adding these three. So x2 double prime will basically exist from minus pi by 3 to plus pi by 3, and again from 5 pi by 3 to 7 pi by 3. x1 double prime will exist from pi by 3 to pi, and x0 double prime will exist from pi to 5 pi by 3. Okay, so let's do that. So once you add it, you will get something like this, and this is only from 0 to 2 pi I have drawn. We know that DTFT is basically periodic with period 2 pi, so it repeats after every 2 pi. So this is omega, this is y of e power j omega, the spectrum which we want. Okay, if I label this as 0, okay, now okay, from minus pi by 3 to pi by 3, this green portion was coming from x2 double prime. This is from here to here, minus pi by 3 to plus pi by 3. Okay, now from, and again it repeats at 2 pi. Okay, so I'll draw it later. The following part comes from x1 double prime, which is from pi by 3 to pi in red color. So I'll do that. Where is the red color? Okay, so and that is the trapezoid part. Okay, so it looks kind of this. Yeah, so this is from pi by 3 to pi, and then at pi the new spectrum that gets added is this blue one from x naught double prime, from pi to 5 pi by 3. Okay, from pi to, so that's the rectangular, like this, from pi to 5 pi by 3, and the center is at 4 pi. And then this green one again repeats, because you see in x2 double prime we had this repeating after 2 pi. So again this triangle will appear, this triangle will appear here. It is centered at 2 pi, and this edge would be 7 pi by 3. This is what your overall spectrum of y of n, which is y of e power j omega, would look like. Okay, and this I have drawn from 0 to 2 pi basically. Okay, and if you look at the options, these options, see option A, actually it matches with option A. So triangular followed by the trapezoid followed by the rectangular, and then again the triangular, it repeats, and each of their bandwidth is 2 pi by 3. Okay, so it's exactly, the option A is exactly the one which we are getting here. So your answer is option A. Okay, so I hope this is clear. Let me know in case of any queries. We'll move on to the next question. I took a lot of time in explaining this. I just want to make sure that you are able to understand. Okay. Okay, now let's go to the second one. Yeah. So second question. So we are given this block diagram again. So basically there is a sequence of z blocks. Z means advanced operator, advanced by 1 unit of time. So there are 3 such advanced blocks, and there are 4 downsamplers, downsampling by a factor of 4. In the last branch, in the branch corresponds to the lowermost branch, basically we are getting y of n as the output. If our input is x of n, is a sequence which is given, then we have to find what is y of n. Okay, so how are we going to do this? This is simple, just arithmetic. This we have to use the downsampling operation and all, and the advanced operator. So what is overall the sequence that we are going to do? um, so the only branch that we need to consider is this, um, from x of n to y of n. So basically how many advanced blocks are crossed in this path from x of n to y of n? There are 3 consecutive advance blocks, z, z and z, and then a downsampling by a factor of 4 to give me y of n. So the signal x of n gets advanced 3 times, so it becomes x of n plus 3 from x of n, and it is further for downsampled by a factor of 4. So basically y of n would be x of 4n plus 3. That's what you are going to get. So this is fairly simple. I'll first draw the figure. This is the block diagram which is given. The uppermost branch is this. Then it goes here, passes through an advancing block. So then in the second branch we again have another downsampler. Then there is another advanced block. Okay, this one. And there is another advanced block, and this is the last downsampler. The output of this downsampler is basically y of n, which we need to find. Okay, and okay, and by the way, there is a small typo here. The sequence y of n, sorry, x of n, the input sequence x of n, it's not up to 9, it's actually a 12 length sequence. Okay, this is just make a note of it. Okay, note, correction, x of n is basically this 1 2 3 4 5 6 7 8 9 10 11 12. Its length is 12. Okay, so please make a note of this. In the question it is of length 9, but it's actually there are 3 more samples as well. Okay, so we'll keep this as our x of n and proceed. Okay, so this is x of n. This is x of n, and now, okay, now tell me what is the signal at this point, at this where I have tick marked. What would be this signal here? Yes, tell me. We are basically considering this path from x of n all the way to y of n. This path we are considering. Okay, so it first goes through a block of z. So I am asking you, what would be the output here at this point? Tell me. I mean, how can you write it in terms of x of n? Okay, so at this point basically your signal will be x of n plus 1, because we have a advance operator, advance by 1 unit of time. If your x of n passes through that block, you will get x of n plus 1. Similarly, at this point you'll have x of n plus 2, and similarly at the lowermost point you will have x of n plus 3. So the reason why I keep on asking on interacting is that these sessions are meant to be an interactive session, just to ensure that you are able to follow and all. But otherwise, if I don't get any participation from your end, then I'll assume that things are fine and I'll just move on. I'll just quickly complete everything. Okay, so this is x of n plus 3, and that gets passed through a downsampler of factor 4 to give me y of n. So essentially this is the final thing which is happening, x of n plus 3 going through downsampler to give me y of n. So your y of n would be basically x of 4n plus 3. Okay, basically downsampling of factor m converts x of n to x of m times n. So that's what I've written here. But anyways, if x of n is this, if x of n is this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I'll actually include this correction in the maybe in the modified question. I'll just do this correction instead of running till 9, it's running till 12. So this is my input sequence with the origin at here. So this implies what will be my x of n plus 3. It's a left shift basically, left shift by 3 units. So I move this entire block to the left by 3 units. That will give me, it remains the same, the values remain the same, but the origin now shifts to this point. It is, this arrowhead now points at 4, right? And cut. So now this is x of n plus 3. Now x of n plus 3 you're passing it through a downsampler. So if you're passing this through a downsampler of factor 4, what does a downsampler do? A downsampler of factor m throws away or discards every m minus 1 samples. Okay, so the downsampler, what it will do is it will always pass the sample which is at the origin. So this 4, this is always passed, but it will discard the next m minus 1 sample, and it will pass the mth sample, and so on. So it selects every one out of m samples, in other words. So here m is 4, so the 3 samples get discarded. So 4 is selected, the next 3 get discarded, and the fourth one gets passed, and so on. So this 5, 6, 7 get discarded. Similarly, on the other left side, these 3 get discarded, and the fourth one is chosen. So 1 out of every 4 sample is passed through. Similarly, these 3 get discarded, and this is chosen. So what are we getting at y of n at the output? So y of n is 4, 8, and 12. Okay, this is 8, 4, 8, and 12. So answer is option B. And in the question, there is one correction in the input sequence. It's not up to 9, it's up to 12. Maybe I'll update the question and then upload it. So anyways, I have mentioned it here. X of n is this. Okay. So this is our y of n, and it matches with option number B, option B. So our answer is option B. Okay. So now moving to the third one. Okay, now third one is similar. Um so here we have basically three branches. In the previous one we had four branches, and here we have delays. We have delays instead of advanced operators, right? Z inverse is there, delay by 1 unit of time. But the strategy would be the same. We'll consider the path from x of n to y of n. Basically, the path will comprise of two delay blocks and one downsampler of factor 2. That will produce me the output. Okay, the input sequence is given here, and then accordingly I can find my y of n. So let's do that. So this is x of n. Topmost branch is just a single downsampler. Then I have this delay block, and here is the second branch, which involves another downsampler. And then I have another delay block, another downsampler. So yeah, yeah, that's the complete. And this is what my output is. I'm getting y of n here. Okay, so again, what would be the intermediate sequences? So this is the path that we are considering, right? This from x of n to this all the way, right? So we'll first write down the intermediate sequences. At this point, after the first delay block, we'll get x of n minus 1, right? Which, if further pass through another delay block of 1 unit, we'll get x of n minus 2 here, right? And then so overall what happens is x of n minus 2 is passed through a downsampling block of factor 2 to give me y of n. So that will be basically x of 2n minus 2. And x of n in our question is given as 1, 2, 3, 4, 5, 6, 7, 8, 9 with the origin at here. Okay. Now from x of n, how do you arrive at x of n minus 2? That's a delaying by 2 units of time, which is right shift by 2 units. So here basically you will get, there will be two zeros and the original sequence 1, 2 that follows. Okay, like this. We are shifting this whole block to the right by 2 units, and then now our arrowhead will point at this location, right? And now this x of n minus 2 is passed through a downsampling factor of 2. So what it will do is it will pick every one out of two samples. So as we know, it will pick up the value at the index n equals to 0. That's always the case. And it will discard the next value. 1 out of 2 it will select. So the second value it will again pick. And similarly the next one it will discard. And it will repeat. So every alternate values basically it will pass. So like this. 5 is passed, 6 is discarded, 7 is passed, 8 is discarded, and finally 9 is also passed. So what are we going to get? Y of n. Therefore y of n is all the samples which are passed, basically, which is this, and the arrowhead points here, right? And if you check with the options, it is option C, 0, 1, 3, 5, 7, 9. So our answer is option C. Okay, these two are similar problems. Okay, now let's move on to the fourth one. What do we have in the fourth question? Again, in the fourth question also we have similar things, right? We have a similar block diagram, but here we have an upsampler, right? We have an upsampler, 3 branches, each with an upsampling factor of 3, right? And we have advanced block as well, denoted by Z. They're adding up together to give me to produce Y of n. Okay. Okay. So now this time basically you have to calculate the contribution of from all the 3 branches, because all the 3 branches are getting added up finally to give me Y of n. In the previous 2 cases, basically you only had to consider the lowermost branch, right? So here in this case we are having actually two adders, as you can see. That's why you need to consider the contribution from all the 3 branches, but the procedure is the same. So I'll draw it. So the question, let me read the question anyway. So this is the block diagram given. Now your x naught of n is given, x2 of n is also given, the output y of n is given. You need to find x1 of n. One of the inputs is unknown to you. That's what you need to find. You know the output, you know 2 out of the 3 inputs. You need to find the remaining third input. Okay, so that is the question. Here you are not asked to find the output is given, but one of the inputs is unknown. That's what you need to find. And again, this notation is like for the sequences, this one of the values it is kept inside a box which corresponds to the sample at index n equals to 0. So I am always using the standard convention that I am using that arrowhead notation to indicate the sample at n equals to 0. Here they have used box, but I'll stick to the arrowhead notation. Okay. So yeah, so let's quickly solve this as well. Again, this is the process is the same. So x naught of n is passed through an upsampler, and then it goes through a advance operator, and now this is the first branch. Then we have x1 of n. This x1 of n is the one which you need to find. That again goes through upsampler, and these two gets added up. Okay, these two gets added up, then the sum of these two passes through another advanced block, and then we have the lowermost branch, which is x2 of n, then a upsampler, and finally the third adder, the second adder, the final adder block, which gives me the y of n. This is the given block diagram. Okay. So like always, we'll mark the intermediate points. Okay. So in this case, um, we are first performing the upsampling. So in the previous cases, we were in the previous problems, we were doing either delay or advancing. That's why we were able to directly write the output of that delay or advance block. But here, since it's an upsampler, I'll use just notation. I can't simply write the mathematical form of that. So I'll use a notation x naught prime of n, okay, to indicate the sequence at the output of the first upsampler. So if this is x naught prime of n, then as you can see, it passes through a advanced block of 1 unit. So the output here after this advanced block would be x naught prime of n plus 1. It gets advanced by 1 unit. Similarly, I will use a notation x1 prime of n for this part, and so these two are getting basically added together. So what are you getting at the output of this adder? This is basically x1 prime of n plus x naught prime of sorry x naught prime of n plus 1. Okay, now this whole thing then further passes through another advanced block of 1 unit. So that will produce, so basically you replace n by n plus 1 everywhere. This gives you this sequence, right? And for the third branch, I'll use the same notation x2 prime of n. Okay, now basically y of n is the sum of these two final sequences. Okay, so I can write y of n as x naught prime of n plus 2 plus x1 prime of n plus 1 plus x2 prime of n. Okay, yeah, this is consistent with our notation, and the information that has been given in the question, we are provided with the information that okay, what is x naught of n, what is x2 of n, and what is y of n. So I'll just write it down here. X naught of n is 1 2 3. Okay, the arrowhead is at this index. X2 of n is 7 comma 7 comma 2, and y of n is also given as 1 5 7 2 8 7 3 4 2. Okay, these are given. So these are, looks a bit clumsy here, but yeah, this is a given information. These three sequences are given to you, and maybe what I can do is, this y of n is given, right? Oh, by the way, the origin is at this location, the arrowhead is pointing here, which means y of 0 is 7, right? Okay, so I'll call this equation I'll label this by equation 1, the given y of n, and this equation which we have written on the bottom, I'll call this equation 2. Okay, both are y of n, right? Alright, fine, so far so good. Now this x of n is x1 of n is the one which we need to find. Okay, we know x0, we know x2, we know y, we need to find x1 of n. So we'll assume, okay, we'll assume it to be some sequence. We'll assume that, okay, it's a sequence with the sample values as some a, b, c, x, y, z, whatever. Since already we have used this x and y notation, it's better to use some other alphabets or literals, like I'll stick to a, b, c, or you can use alpha, beta, gamma, whatever. So we will assume that it's a sequence a, b, c, and because you see x0 and x2 both are of length 3, so that's why I'm choosing x1 to be some length 3 as well. And even in the options also, here you see all the 3 options are of length 3 only, so I can assume that, okay, it's some sequence ABC, okay, of length 3. So I'll do that. Okay, so go to the next page. So I am assuming let x1 of n, which is our unknown sequence, be some sequence a, b, c. These values a, b, c I don't know, with, let's say, the arrowhead pointing here, which means x1 of 0 is a, right? Okay, and now we will go step by step. We'll go back to the diagram and we will gradually arrive at y of n. Okay, so this one. Okay, so we'll first find y x naught prime of n, then we will find uh, basically we'll go basically branch by branch. We'll finally, uh, equate this. Actually, if this equation 2 which I have labeled, so this involves x naught prime of n plus 2, then x1 prime of n plus 1, and x2 prime of n, right? We'll compute these three and add them together. Of course, x1 is not known to us, that's why we assume some variables a, b, c, but we can still perform the shifts and all variation and all operations on them. So it will be a function of a, b, and c, the final sequence that you are going to get. But y of n is given. You see equation 1, it is given. So then we can compare those two to calculate the value of a, b, and c that's valid, that's consistent with the given information. So we'll do that. Okay. Um, so okay, we assume that x1 of n is this. Now we'll go step by step. First thing, y naught prime, sorry, x naught prime of n. What is this? X naught prime of n is this thing, this guy. So which is nothing but x naught of n passed through a upsampling block of 3 factor. X naught of n I know, it's basically this sequence 1, 2, 3 with arrowhead at 1. So upsampler, what it does, here we are in the time domain. So in time domain, what's the effect of an upsampler? It introduces it adds basically L minus 1 zeros between every sample. So here it will add 2 zeros between every 2 samples. So that way I can get x naught prime of it, right? Because I need x naught prime of n plus 2 to get y of n, right? Because that's given in equation 2. So I'm going step by step. Okay. So first x naught prime of n, by the property of upsampler, basically what it does is, in the sequence 1 2 3, it will introduce two zeros between every sample. So this, see, between 1 and 2, two zeros got introduced. Similarly, between 2 and 3, we will have two zeros. And origin stays at this position. Okay. This is x naught prime of n. Now, what do we need to find? See, to find y of n, we need to basically find this thing, x naught prime of n plus 2, this guy. So we got x naught prime of n. Now we need to find x naught prime of n plus 2. So how do we do that? It's basically left shift by 2 units. So x naught prime of n plus 2 will be the sequence 1 0 0 2 0 0 3, but the arrowhead now points to this location, right? Okay, this is one component that we have found. Okay, this is x naught prime of n plus 1. This is one thing which we have found. So this part we have got, this guy we have found. Okay, now remaining is this one and this one. Once we have the values for those two, we can add them up. Okay, so let's do that. Now we need to find x1 prime of n plus 1 and x2 prime of n. So let's do that. So what is x1 prime of n? See, x1 of n is the unknown one, which we assume to be ABC, and x1 prime of n, if you go back to the diagram, is this guy. So which is basically x1 of n passing through a upsampler of factor 3, right? Again, we'll use the same concept. We'll introduce two zeros between every two sample to get x1 prime of n. So this would be nothing but the same ABC, it remains, but between every two samples we'll have two zeros. This, and but we need to shift it again by 2 units to the left, because you see here this term, this is x1 prime of n plus 1. So we need this. So for that we need to left shift this by 1 unit. So this is x1 prime of n plus 1, which is nothing but a 0 0 b 0 0 c, with the arrowhead now pointing at this location. So I'll put this in a box as well. Okay, right, and now what's the remaining term that we need to find? This guy, this one, x2 prime of n. And how do we find x2 prime of n? Well, x2 prime of n is nothing but sitting here, so it's x2 of n pass through an upsampler of factor 3. So again the same thing, we'll introduce two zeros. Okay, right, so x2 prime of n, x2 prime of n, x2 of n we know, x2 of n is given in the problem, this here 772, this one. So we'll introduce two zeros between every sample here. So we can write it as 7 0 0, then again 7, again two zeros and 2. Okay, arrowhead points here. Again I will put this in a box. Okay, yeah, so these three sequences which are enclosed in the box are the three sequences which we want to add together. That will give me y of n, because that's what equation 2 tells me, right? So we'll add them together, y of n. If we add them together, you will get, so basically you take these three sequences and add the, add the samples corresponding to the that particular index and so on. Okay, so you can do that. So what you will get is verify 1a7 2 b7 3c2 with the arrowhead pointing at this location. This is what you are going to get from adding these three. And how can I write this? This is basically what equation 2 tells me, because that's the sum of these three sequences enclosed in the box. Great. Now again I'll use I'll label this by a new equation 3, let's say. And this equation 3 which I got, so this is still, we need to find this a, b and c, right? But in equation 1 I know complete picture of y of n. I know all the uh, samples. So then I can now compare equation 1 and equation 3 which I just obtained to find the value of a, b and c. And once I know a, b and c, I can find this x1 of n which is asked in our question, right? So that's it. So let's do that. So what I'm going to do is comparing equation 1 and 3, we would get, so you see this a is sitting here at the second index, and now if you go back to equation 1, at the second index you have the element 5, so a is nothing but 5. Therefore you can do the same thing, you can just match them, equate them index by index, and subsequently find the values of a, b and c. So you will get a equals to 5, b equals to 8 and c equals to 4. And therefore now my x1 of n, which I assume to be sequence a, b and c, is now known to me. This is 5, 8 and 4. That's it. So that's our answer, which is nothing but option B, 584. Again, this box is the same thing. I have just used this arrowhead notation. So this is matching with option B. Okay, great. So again, I'm assuming just you are clear with all the steps. So until and unless I don't receive any question or anything from your side, I'll assume that it's fine. Okay, great. So now going to the fifth one. Fifth one is pretty simple actually. Fifth one is, you can straight away tell this. So which of the following corresponds to an impulse response that is not purely real? Okay. So in our options, what we are given is the spectrum. It's basically the DTFT which is given here in frequency domain. Now it has been asked that, okay, which of these spectrums corresponds to an impulse response that is not purely real? Okay, So impulse response means that h of n in the time domain, and we know that for a real impulse response, from the property we know that if we have a real impulse response, if h of n is real, then the frequency response, which is capital H of e power j omega, is conjugate symmetric. That's what we know. Or in other words, what this conjugate symmetry implies is that in the frequency domain, the spectrum is actually symmetric with respect to the vertical axis. Okay, so that will be satisfied for a real impulse response, right? So all you need to check is that, okay, whether it's symmetric about the y-axis or not. If it is symmetric about the y-axis, then you can conclude that, okay, the impulse response is real. But if it is not symmetric about the y-axis, then by the way, this is just the magnitude response that we are looking at. Now if the magnitude response is not symmetric about the y-axis or the vertical axis, then you can conclude that the impulse response is not purely real. Okay, that is the idea. So you see, just observe the given options. Option A is looks like this. Okay, so the spectrum has, there are two um, copies, or whatever, two triangles are present in the spectrum. One is in the positive side centered at W1, and the other is in the negative side. It's just symmetrically opposite to the one on the positive side. It's centered at minus W1, so it's symmetric about the vertical axis. Clearly we can see. So this is symmetric about the vertical axis. That means its impulse response is purely real. Okay, so option A is not the right answer. We want to find the one which corresponds to an impulse response which is not purely real. So this symmetry will not hold there. So again, now option B, if we check, it is again, you see, it's symmetric about the y-axis, because it's just as if we are taking the mirror image, right? These two things, these two blocks which are sitting here on the positive and negative side, they are just the mirror images of each other. Okay, this is again symmetric, so this is a real impulse response, so it's not purely real or something like that. So option B is also not the right one. Now what about option C? So you see, option C, if you observe the spectrum, this is not symmetric about the vertical axis. These two copies are not the mirror images of each other. You see, this is not symmetric. The shape is not exactly symmetric. It's not like that, right? Whereas option D, if you go to option D, it's again symmetric. So it's conjugate symmetric frequency response. Therefore, the impulse response is purely real. But in option C, that is not the case. Option C, the frequency response is not conjugate symmetric. So therefore, we can tell that its corresponding impulse response in time domain h of n is not purely real. Okay, so straight away you can write, just by observing the spectrum, that okay, option C is the one which corresponds to a impulse response that is not purely real. So option C is our answer, right? Option C is our answer. So yeah, the main thing to remember is that for a real impulse response, the frequency response is conjugate symmetry. So I'll just write it. For a real impulse response, the frequency response is conjugate symmetry. Okay, and why it actually comes from the property. You can actually verify it as well. So maybe quickly what I can do is, you know that h of n is the impulse response, and if you take its DTFT, discrete time Fourier transform, you get capital H of e power j omega, right? Now for a real impulse response, for a real impulse response, which means that if h of n is real, then we know for a real quantity, if we take the complex conjugate of a real number, it becomes the same, it remains the same, right? Because it does not have any imaginary part. So for a real impulse response, h of n is the same as h of n conjugate, complex conjugate. The star denotes complex conjugate, right? So um, what's my h, capital H of e power j omega from the formula of DTFT? I know that, okay, this is, I'm considering a discrete time scenario, h of n, so that's why the formula for DTFT is n running from minus infinity to infinity, h of n e power minus j omega n, this thing, right? Now in this summation I can replace h of n by h star of n as well, because it's real, right? So if I do that, this is, why can I write this? Since h of n is the same as h star of n. Star is complex conjugate. So now what do we get? This is nothing but summation n running from minus infinity to infinity. I can rewrite this as h of n times e power j omega n whole conjugate, because if you take the conjugate of this whole thing, the first term will be h star of n, and the conjugate of e power j omega n is e power minus j omega. So I can rewrite it like this as well, right? Okay, now what I am doing is, I can also rewrite this as, I can take this summation, basically summation n running from minus infinity to infinity, inside the bracket as well, because that follows from the linearity, right? Because what I'm saying is, if you have some uh, z1 conjugate plus z2 conjugate plus z3 conjugate, so this is nothing but your summation zi conjugate I running from 1 to 3. This is the same as, adding them first without taking conjugate and then taking their whole conjugate, right? Which is the same as summation zi I running from 1 to 3, that whole conjugate is the same thing. This thing and this thing, they are the same, right? So that property if you use, so this is just aside, okay, this is just a rough, I mean, maybe, yeah, this is just for a illustration purpose. This is rough work, okay? Okay. So I can put this summation inside. That's what I wanted to say. So okay, so I can rewrite this as taking this summation inside this. Okay. Now, what is this term sitting inside? This is summation n running from minus infinity to infinity, h of n e power j omega n. It's very close to the DTFT formula, except that usually in DTFT formula we have e power minus j omega n as the multiplicative factor, but here we have e power j omega n. So it's as if omega is replaced by minus omega, that's it. So this term is nothing but, inside the conjugate, is nothing but capital H of e power minus j omega. You just replace omega by minus omega, that's it. And you take, so, and you are taking the conjugate that of whole thing, of that whole thing. So overall what you are going to get is capital H star of e power minus j omega. Okay, this is the property that is satisfied for a real impulse response. So what we saw is that basically if I write it in a box, h of j omega is nothing but h star of e power minus j omega. For real impulse response h of n, this is valid. Okay, this is what the complex I mean the conjugate symmetry property tells us. That's a short proof for that I have shown you. Okay, right? So that's why we are able to claim that okay, it will be complex, it will be conjugate symmetry in the frequency response. And we just saw that option C is the one in which the conjugate symmetry property is not satisfied. That's why we are able to claim that okay, the corresponding impulse response is not real, not purely real, right? Okay, good. So now moving on to the next one, which is sixth one. Okay, this is the sixth question, and this is actually directly from the lectures as well. So yeah, you just look at the question. Yes, is there any question? Okay, no. Okay, so yeah, so what do we have here? We have basically m number of branches, you see, from all the way from at the output what we are getting is the DFT coefficients, basically capital X naught of n, capital X1 of n, so on all the way till capital X m minus 1 of n. So on the left hand side we have um, m minus 1 advanced block, this Z block setting. Okay, so our input is getting uh, advanced by 1 units successively to the m parallel branches, which are going as input to our WDFT matrix. So this is a DFT matrix of dimension capital M by capital M. It's a square matrix, and FDFT matrix was discussed in the lectures as well. How does it look like? Basically, you take the mth complex root of unity if it's a m by m DFT matrix, and you can form the DFT matrix in a nice structure. Okay, and that matrix acts on that incoming vector, which is a vector of the elements x of n plus 1, x of n plus 2, and so on till x of n plus m minus 1, to give me some other output vector, which is capital X naught, capital X1 all the way till capital X m minus 1. And now this the basic notation is that okay, we define that x of n, the sequence has a z transform denoted by capital X of z, and this hk of z is the ratio of xk of z and x of z, meaning that it is the transfer function associated with the kth branch. Basically, xk of z is the z transform that you obtain at the kth branch, at the output of the kth branch. There are m branches, and in the kth branch you are obtaining capital Xk of z as the output z transform, and the input is x of n, so input z transform is capital X of c. So from the input to the kth output, you are getting a transfer function which is capital H of capital H subscript k of z. That's the notation. Okay. So for instance, if you are considering the first branch, which is corresponding to k equals to 0, it becomes capital H subscript 0 of z, h naught of z, right, which is capital X naught of z by x of z. Similarly, if you consider the second branch, which corresponds to k equals to 1, it will be capital H1 of z, which is x1 of z by x of z, like that, so on. Okay, this is the notation, and then if this is the case, then which of the following is true? Okay, we are given some options which actually relates this transfer function of the kth branch, which is hk of z, as the to the k equals to 0 at the branch. Basically, you see there's a relation between the hk of z and h naught of some function of z, right? So how are they related? That's we are asked. Okay. So let's check that. We have seen this in the lectures, but anyways, we can work it out again. So for this, I would encourage you to refer to lecture 17. In week 17, in week 5, we have gone through lecture 17. Just go back to your lecture 17. These things have been discussed. Okay. So I'll read out the figure first. X of n So this is also filter bank, you see. Okay, there is a first incoming branch like this. Yeah, I'll extend this somewhere till here. Then this is the first branch. Then we have an advanced block like this. We have another advanced block. Okay, so the first branch is just a straight line. There's no operation being done here, so this is actually same as x of n, which I will use notation s naught of n. So that's correspond to the 0th branch, or the basically first branch. So s naught of n is same as x of n. Now you take the second branch, so it gets advanced by 1 unit of time. So you will obtain here x of n plus 1, and I'll call this as s1 of n. Okay. Similarly, for the third branch, you get one more advanced block, so you get x of n plus 2, which I'll call it s2 of n. And now you know the relation, right? Like x of n plus I is same as si of n, like that. So, and it's consistent with the notation which has been used in the lectures as well. That's why I asked you to refer to lecture 17. So this parallel branches continue all the way till the mth branch. So we will have the m minus 1th advanced block. Okay, advanced block that yields me x of n plus m minus 1, which is the same as s of m minus 1 of n. Fine. This whole thing is fed to a DFT matrix. It's a vector basically. It's a vector which is fed to a DFT matrix W. W is your DFT matrix and it is of dimension m cross m. Because the input vector is of dimension m cross 1, there are m branches. So the matrix, it's a square matrix by property of DFT matrix. So and it's also like other properties are also there, like orthogonality, unitary, and so on. So therefore it has to be of dimension m cross m to act on a vector of dimension m cross 1. And now the output, we have m branches, capital X naught of n, capital X1 of n, capital X2 of n, so on all the way till capital X m minus 1 of n, right? Okay. Now the notation is like this: x of n has a z transform like this. Now the kth, the transfer function for the kth branch basically is denoted by hk of z, which is nothing but the xk of z by x of z. This is given. Then we need to find, okay, we need to check the relation between hk of z and how is it related to h naught of z. So now you see, I have used this s naught s1 si of n, right? The relation between si of n and x of n is as follows. I have already mentioned it, but I'll write it again. So here, this si of n is nothing but x of n plus 1, right? And here I basically runs from 0 to m minus 1, corresponding to the m branches. Okay, right? So if this is the case, so you see si of n is actually the shifted version of the x of n, shifted by I units. So if you take the z transform on both sides, this is capital Si of z, which gives me, by property of z transform, this becomes z powered I capital X of z, right? Okay. And now we know that now what's happening is that this Si of z, these Si's are fed to the DFT matrix. So the DFT is computed and we get the output vector, right? So we know that the DFT equation or the formula is given by the coefficients. These are the DFT coefficients, right? A capital Xk of n. So this is given by summation I running from 0 to capital M minus 1 Si of n W suffix m to the power ki, where W suffix m is nothing but the mth complex root of unity, which is e power minus j 2 pi by capital M. Okay, that's what is happening basically. You have an incoming vector of Si of n, right? It's an m by 1 vector, and this matrix, which is m by m square matrix, is acting on that vector to produce another vector, which are the DFT coefficients. So what happens here? So what is xk of n? It's basically the kth row of the matrix capital W, the DFT matrix, multiplied with the uh, input vector, which is like s0 of n, s1 of n, and so on all the way till sm minus 1 of n, right? So that's what is happening. So you get some linear combination of that. It's basically the same thing. It's taking the inner product of the, or the dot product pointwise multiplication of the kth row of the DFT matrix and the uh, input vector. That's what is happening here. That's what I have written here. And again, go back to the lectures, everything was discussed here. So now if we take, so taking Z transform on both sides, what do we get? So xk of n now becomes xk of z, and just a second, yeah, where is that? Yeah. So this is like xk of n. We are taking the z transform of this, so we are getting capital X of capital xk of z. Okay, to get, and on the right hand side what happens is, you have summation I running from 0 to capital M minus 1. So you take the z transform of Si of n to get Si of z, right? And this term remains the same because it's just a linear combination. It's independent of, your n. So you just, by property of linearity, you can just write this. Basically, if you have a linear combination of some sequences, then if you take the z transform of that entire linear combination, you get the you just take the z transform of the individual sequences, and you get the scaling factors remain the same. You get a linear combination of these z transforms as well. So that holds by virtue of linearity. And now what? Now Si of z is known to us, which is z to the power I times x of z. So I can rewrite this as xk of z equals summation. So I'm replacing Si of z by z to the power I times x of z. This thing, right? Now what I can do is, so you see summation, the index of summation is I. I is the variable which runs from 0 to m minus 1. But this term here, x of z, is a term which is independent of I. So I can simply bring this term out of the summation. The rest of the two terms, which is z power I and wmk to the power I, they are both dependent on I. So they are the variable terms. So I can just simply bring x of z outside, so which is x of z times summation I running from 0 to n minus 1 this. By the way, this WMK is nothing but WM to the power K basically, right? Okay. Now you see, now we have a complete input output relationship. So this is xk of z. What is that? That's the output of the kth branch. What is x of z? That's your input. So this term here is nothing but the transfer function of the kth branch, which is, as per our notation, capital Hk of z. So we have found Hk of z, the form for Hk of z. So I'll go to the next page. So we just found that Hk of z is nothing but summation in running from 0 to minus 1 this thing. So I just written the same thing here. Okay. 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 Now on the other side, let me do a demarcation like this. Now if I put k equals to 0 here in Hk of z, what do I get? H naught of z. What is H naught of z? Basically put k equals to 0 here. So on the RHS, what you get? This. So z times Wm to the power k. Wm to the power k. For k equals to 0, it becomes Wm to the power 0, which is nothing but 1. So this gives me basically effectively z power I. That's sufficient. So that's nothing but, so this is a finite GP series, right? 1 plus z square plus so on till z power m minus 1. Correct? Okay. And if you expand this one, hk of z on the left hand side here, so what do you get? This is nothing but 1 plus basically for I equals to 0 you get 1, for I equals to 1 you get z times Wm to the power k. For I equals to 2 you get z times Wm to the power k the whole squared plus dot 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 till when I is m minus 1, the last value, which will give me whole to the power m minus 1, this thing, right? Now if you just label this by equation 1, and if I label this one on the right hand side by equation 2, if you compare these two equations, you can relate hk of z with h naught of z. You see the form is the same for both of them. Both are, you know, sum of m terms, right? And the pattern is also same. 1 plus x square plus so on till x power m minus 1, of that form. Only that x term is different in both the cases. So if you compare equation 1 and 2, you can relate actually hk of z with h naught of z as follows. So if you basically if you replace this z here for h naught of z by z times Wm to the power k, you get hk of z. That's what the thing is. So in other words, what I am saying is, this Z replace Z by Z times Wm to the power k. If you do that, you get Hk of Z. That is the observation. So the relation is that this is the relation. And how did I write this? I basically compared equation 1 and 2 to write this. Okay. So if you check the options, option A is the right answer, right? Yeah, it is matching. Option A. Option A is the right answer. Okay, we're done with the sixth one. Now let's go to the seventh one. Yeah, just read the question. Okay, so we are given two figures. Okay, the figure on the top is a chain of some filters and some downsamplers, right? And it is mentioned that this figure on the top, this system is effectively the same as the system uh, which is represented by the figure on the bottom, which is just one filter some g of z followed by some downsampler of factor n. So this whole thing on the figure on the top is effectively equivalent to the figure on the bottom. So if that is the case, then you are asked to find what is g of z, what is this single filter which is doing the same job, the effective filter which is doing the same job as all the rest of the filters on the figure on the top. And we have seen these kind of problems. In fact, in our last session also we have discussed a similar problem. Whenever you have this kind of a problem, one of the key elements that you want to use is the noble identities, basically, because what's going on here, you see there's a chain of some filters and some downsamplers, but they are kept alternately. If you observe the figure on the top, so there is a filter which is followed by a downsampler, then again a filter followed by a downsampler, and so on. And this simplified figure on the bottom is just a single filter followed by one downsampler. So the key is to, if you are able to group the downsamplers together on the right hand side, and if you are able to group the filters together on the left hand side, you are done. You can land up in the form which is the simplified form which is given. So for that, the best way to use the tools that are known to us, and one of them is essentially the novel identity. So we'll use that. Okay, it's a very easy problem. So I'll just first draw the figures. um, we have first filter h naught of z followed by a downsampler, then we have another filter, another downsampler, one more filter, and this is the final downsampler. This is the complete picture, and it says that this is equivalent to one single filter G of Z followed by one single downsampler of downsampling factor n. Now you need to find G of Z. The key is to use noble identities. Okay, so we'll do that step by step. Let me again start from the given long chain. Okay, I'm manually redrawing it, but I'm not using any tool to just copy it. Maybe it would have been an efficient way, but still let's redraw it anyways. So this is okay, so this is H0, H1, H2, and finally 4 downsampler. Okay, that's it. Now we will simplify this to convert to the simplified form. So for that, first what we can do, we can pair these two together. We can actually apply the noble identities on these two blocks. So you see you have a downsampler followed by a filter. Okay, and this is indeed an efficient representation, because we want our downsampler to be done first, because that essentially throws away or discards some of the samples, and then do the filtering and then do the computations on the remaining values only. Rather, if you do the, so this is the efficient form actually, which minimizes the wasteful operations. Rather, if we have a filter and then if we are doing the downsampling, it's not that efficient, because you are doing the processing and all, computation and all, and in the end you are anyways throwing away the samples, m-1 samples. Then what's the point of performing any operation on those samples which are anyways going to be discarded, right? So that's not the efficient one. So we can use the noble identities to represent these two blocks together. We can actually exchange their order. So whenever we are exchanging their order, remember this filter now will come to the front and it will become h2 of z power m basically. So here m is 2, so it will become h2 of z squared, and the downsampler will just go in the second position. Their places will be swapped and just the filter will be modified, right? But that one is not the efficient representation. But in our case, we are making use of the noble identities. It is in order to arrive at a compact form, which is the simplified form. We are basically pushing our filters or the transfer functions to the left side, and we are grouping the downsamplers to the right side. Okay. So if we do noble identities here, what we are going to get is the rest of the blocks remain the same. Here this filter comes ahead and it gets modified to h2 of z squared, and now this downsampler goes after the filter and the last block as it is. Okay, right. Okay, by the way, this is a downsampler notation, right? This is downward pointing arrow. um, like this. Okay, so Yeah, now what you can do is you can see you can group these two downsamplers together. Basically, if you have a downsampler of 2 and followed by a downsampler of 4, we can combine that 2, and that's equivalent to a downsampler of factor 8, the product of them. And similarly, we can actually group these two transfer functions together as well, because they are in cascade, so we can just multiply them together. So what are we going to get now? H naught of z so now this becomes product of h1 of z and h2 of z squared, and this effectively becomes downsampling by 8. Okay, and again now once more we can use the Nobel identities for these two blocks. So that leads us to h naught of z. Now this filter comes in front, and it will basically become h1 of z squared times h2 of z to the power 4 effectively. Yeah, so this, and now this downsampler goes to the right, and we have this last downsampler here. Almost done. We can now again similarly group these two downsamplers together and group these two filters in cascade together. Basically, we'll multiply them. Um, so I'm going to the next page. So that gives me h naught of z times h1 of z squared times h2 of z to the power 4. So what I am doing is here is that I am multiplying these two transfer functions together because they are in cascade, and similarly we are multiplying these two downsamplers which are in cascade. So effectively 2 times 8 would be 16, and that's it. So you see we have arrived at our simplified form, which is a single filter. Now this effective filter is actually which was given on the second figure, which was denoted by some g of z, right? And this was actually denoted by your m. So go back to that figure, this figure, g of z followed by m downsampler. This is the thing. So we found that g of z is h naught of z times h1 of z squared times h2 of z to the power 4. That is the relation. Now if you check the options, it is option B. Option B. Okay. So this is question number 7, and now for question number 8. Question number 8 is basically an extension of the question number 7 itself. So we are asked to find what is the value of m, capital M, in the previous question. So we have calculated, right? We have found that m is equal to 16 here. So we have already done that. This is continuation of question 7. So m equals to 16, we have already calculated. And if you look at the options, it is option D, m equals to 16. So option D. Okay, good. So now finally, the last question for today. Okay, there are two figures given. No need to be scared of these figures. It's pretty easy. So there is figure 1 on the top, which is one implementation, and there is a second figure which is another second implementation, and we are given two statements, and we are asked whether okay both the statements are true or not, whether statement 1 is true and statement 2 is false or not, like that. So maybe I can zoom out this one a bit so that you can see both the figures simultaneously. Yeah, I think this is fine. Okay, so what does our first statement tells us? Let's see. The first statement is telling that figure 1 and 2 are both synthesis filter banks. So if you look at both figure 1 and 2, um, what is happening here is that yes, these are indeed, both of them are synthesis filter banks, because in synthesis filter banks what we do is basically we combine the signal components together to synthesize a new signal, right? So that's what is happening here. You see, you're for at the input side you are doing some processing, some before the IDFT for the parallel branches, and then at the output side you are basically combining them through some sequence of filters or upsamplers, whatever, uh, and some delay operators, and finally you are adding them up, you are combining them up to get a resultant signal which is some x hat of z, right? So some x hat your signal which you are getting, we are synthesizing that signal by combining the components together. So yes, both figure 1 and figure 2 are representations of synthesis filter banks. So statement 1 is true, right? Simple. Now what about statement 2? Statement 2 is saying that figure 1 is more efficient than 2 than figure 2 in implementing synthesis filter banks. Okay, statement 2 is claiming that figure 1 is more efficient than figure 2 in respect of the implementation of the synthesis filter banks. So is it true or not? So let's look at it. So in figure 1, basically the figure on the top, you see what you have done is you have done the upsampling first. You have kept this upsampler by a factor of m. You see, just you have done this thing on the very beginning, and then you have done all the computations and processing on them. You have done the IDFT, you have done the filtering, you have done the delaying, and all those things, and adding and everything. So now what does an upsampler do? An upsampler introduces, basically if it's an upsampler of factor m, it introduces m minus zeros between every samples. So you are doing the upsampling at the very beginning, and you are essentially introducing those m minus 1 0 valued samples, and then you are doing all the computations on those zero valued samples, which is not an efficient implementation, right? Why would you waste your resources in performing computations on the zero valued samples? That's pointless. So this is not an efficient implementation. Whereas on the figure 2, the figure on the bottom, you see that the upsamplers are placed towards the end. You are doing all these computations, IDFT and the filtering first, and then you are doing the um, upsampling, because once your computations are done, then you can simply do the upsampling and introduce some zeros, because you are not performing those heavy computations on the introduced zeros in this case. So of course, this figure 2 is the one which is the more efficient implementation of the synthesis filter banks, right? So statement 2 is actually false, because statement 2 is claiming that figure 1 is more efficient than figure 2, but that's not the case. The reverse is true. So our conclusion is that statement 1 is true, but statement 2 is false. So which is matching with option B. Okay, so I'll just write it here, justify our answer. Okay, this is question number 9. So the first part was like to check whether both are synthesis filter banks or not. Indeed, it was true. Both of them are representations of synthesis filter banks. So in both figures 1 and 2, the signal components are combined together. They are combined together to produce a, or to synthesize a new signal. So therefore it implies that both are, so this is the symbol for implies. Okay, so this implies that both are synthesis filter banks, and which means that statement 1 is true. Okay, that's what statement 1 claimed. And now regarding statement 2, we saw that that's not correct, because the reverse is true. Figure 2 is actually more efficient than figure 1, because the reason I have already mentioned, because this figure 2 actually is avoids the unnecessary computations. All the wasteful computations are avoided here. It avoids the unnecessary computations on the zero valued samples, which are introduced by the upsampler. Introduced by the upsampler. Because in figure 2 you are placing the upsamplers towards the end. So you're doing all the computations beforehand, and then you are introducing the zero valued samples. So that's efficient. So therefore, statement true is actually statement 2 is actually false. Okay. Okay. And that actually leads us to the conclusion that statement 1 is true and statement 2 is false, which is matching with option B. So with this we come to the end of today's session. I hope it helped you to get some insights on solving the problems, and will help you in solving the assignments. So thanks for joining, and we we can meet again on next Friday, 6 p.m. So yeah, thanks. You may sign off and stop the recording.